I have to say that Laura has been one of the original inspirations behind this idea, because her seminal work on validating fuel moisture, stuff moisture, specifically using remote sensing, has been something that's captured our interest for the last few years. And then we had a really interesting webinar last summer with Tim Lenham from Canada and Shalene Kresnik-Hayes, and again we're using Laura's data and looking at it, and keep thinking that there is something here that we really could use in wildland fire management in high latitudes. And so once again we've asked Laura to talk to us about this idea.
So are you ready for me to begin then?
Yeah, go ahead.
Okay. So I'm excited that you're interested in this, because this is some work that I've been doing for a while, and really have strong interest in it. And I ended up doing my PhD on this, finishing up last year. So anyway, I'm gonna. My name, by the way, is Laura Bourgeau-Chavez. So no problem with not pronouncing that. I know it's a mouthful. So the talk is about remote sensing subsurface organic moisture, state of the science, sensors, and potential application to fire danger index validation. So I'm going to start by just showing how satellite remote sensing may be useful for fire danger assessment, and then talk mostly about active microwave sensors, but passive and active are really the only two sensors that are going to give you subsurface soil moisture information. Passive sensors are coarse resolution, and examples of current ones are SMOS and SMAP that was just launched. And then the high resolution ones, some of the older ones that have been around for a while are the European Space Agency ERS-1 and 2 and ENVISAT, and then more recent ones are RADARSAT-2, PALSAR, and PALSAR-2, and the Sentinel-1 is the follow-on to ERS, which was, I think, launched last year. So I'll talk about, in the middle here, about the high-resolution radar or synthetic aperture radar or SAR data that I've been evaluating to improve fuel moisture monitoring, mostly in Alaska, but also considering Canada. And some of the early work I did was with those older sensors that just had a single frequency, single polarization, so just one band, kind of limits your applicability to creating a spatial map. And then talk about, this is really my PhD work, looking at polarimetric systems that give you 4 channels, 4 polarization, or 2 polarizations, but both send and receive returns. You have 4 channels, and then you have phase information that allows you to understand something about the structure. So it improves your mapping capability. And then I'll talk a little bit about potential of the new NASA SMAP, which is a combined active and passive microwave sensor. So whereas these old, like SMOS is 40-kilometer resolution, and some of the older ones are also 36 to 40 kilometers, it combines both the coarse resolution passive with a high resolution active sensor to get 9-kilometer resolution. So it's a kind of an intermediate resolution there. So I'm sure everyone on the call knows about the Canadian Fire Danger Rating System. I'm not going to go into that, but just talking about the limitations with any point source system, you really can't, you can interpolate between them, but patterns of rainfall are so sporadic and discontinuous that you can't really get an accurate measure between those points. And then I've talked extensively with Randy and other fire managers about problems with spring startup values for drought code in particular in Alaska, as well as midsummer ground thaw that's not accounted for in the weather base. And on the right, here's the remote sensing kind of advantage. This is an example of a live shrub moisture product from AVHRR, but it's spatially continuous, gives you a more direct measure of moisture. This is of the shrub canopy. you want the ground surface again, you're going to need those longer wavelengths. This is just giving you the canopy moisture, but it gives you more of a spatial map of what's going on. So those AVHR is visible in infrared, micrometer scale frequencies or wavelengths, and it's more sensitive to things going on like at the cellular level in the leaf. So very, very tiny changes, so it can get moisture in the leaf as well. Whereas the microwave or the radar bands are way out in the millimeters to meter wavelengths, and they're more sensitive to structure, and they're able to penetrate a canopy depending upon how long the wavelength is, and interact more with that soil and get at the deeper soil condition. So I talked a little bit about the active and passive. They're very long wavelengths. They're both not only sensitive to that moisture, though, but also to the vegetation structure and surface roughness. So you have to kind of tease out the moisture information from that. The microwave, the reason it's so coarse is that it's measuring naturally emitted energy from the Earth, and it's a function of both the object's temperature and the moisture properties. And it's coarse because the field of view has to be very large to detect the low emittance from the Earth. So here's just an example of SMOS product, 40-kilometer resolution. It gives you global data on high repeat, which is the advantage of it, but then it's very coarse. So active radar sensors, or SAR sensors, they have their own energy source that they illuminate the Earth, and they measure the energy that's backscattered from the ground. So the strength of that signal is a function of both system parameters and features of the ground, of the image, things within the image. So the system parameters include that wavelength we talked about and the polarization, but also the imaging geometry. And SARs are side-looking, so depending upon the angle you're looking at, you see a different type of scattering occurring. And then the image elements, again, are the surface roughness, the structure and geometry of vegetation in this case, as well as the dielectric constant, which is related to the moisture status. So here's an example of ERS2 sensor, which had 30-meter resolution. So down on the bottom, wet and a dry date of the Delta Junction area, and you may recognize the fires. The left one, well, actually they show up in both, bright on the wet date, dark on the dry date. The Donnelly Flats 99 fire, and then in the middle there's the Fort Greeley 87 burn, and Nagadukovich Creek 1994 fire on the right. And here's a little schematic here showing the different wavelengths. So these are C-band, which is about 6 centimeter, to about 5.7 centimeter wavelengths. So if there's a forest canopy there, unless there are gaps in it, the energy is just going to bounce off of that canopy. But
Laura, can I ask a question?
Sure.
So this is a good slide to think about this question. So I've seen a couple SMAP proposals go by, and the assumption is that the SMAP sees moisture content in the top 5 centimeters of soil. And my understanding is it's been calibrated for mineral soil. What's your guess in terms of, do you think SMAP will provide information about organic soils? And I don't think it's been tested yet, so what do you think?
Well, it hasn't been tested yet, but it is the L band. So here at C band, with short wavelength, but these soils, in my picture here, which I'm sure you're familiar with, they're very low bulk density, and especially when they're drier, you're going to get greater penetration of those. So it's going to be longer than a wavelength. So theoretically, the wavelength will penetrate up to the depth of one wavelength. But in our case, we found for C-band that we had better correlation with 12-centimeter moisture than we did with 6. And theoretically, it should only go to about 6, but it's going much deeper organic soils. So L-band should go even deeper than that. I've done some work with L-band, and we tend to measure at 10 or 12 and down to 20 centimeters for L-band, and it seems to correlate pretty well with the 20-centimeter depth. So I hope that answered your question. This map is L-band, so the thing about the passive, though, is it's emitted what's naturally emitted, so it's more of a surface. So when you combine those two, 5-centimeter may be more accurate. I'm not really as familiar with passive microwave as I am with active. But they will have some other products. They'll have well, it's more researchy, but there will be a radar only at 3-kilometer resolution, and that definitely should penetrate deeper, down to about 20 centimeters. So I think I went over this slide, and the other thing I wanted to show on this is the size of an image. It's only about 70 to 100 kilometers, one image, and then your repeat maybe 3 weeks from this date. So although it's very useful in showing you moisture in those burned sites, the repeat is pretty low resolution. But using that C-band and using those burn scars, I developed 3 methods to assess fuel moisture. I'm just going to show the first one, just what we call large area monitoring, so it kind of reduces the variability, the heterogeneity within a region, so that you just average all of the backscatter down into one value, and then you're able to create a correlation that way. So this is a question I get all the time about why are we using burn scars? They already burned for fuel moisture, but the answer is that we've removed, the vegetation has been removed. So at C-band, which doesn't penetrate that canopy as well, you've removed the canopy so you can actually see what's going on in the ground. And we've demonstrated through field studies that although the magnitude of the moisture, the actual moisture values may be different, the trends are the same in the burned and the unburned sites. And we've been able to correlate the backscatter in that burn to the drought code directly. So here, those 2 image mosaics of East Central Alaska showing multiple fires. So that's the other thing. You can see these areas for long time periods and use the backscatter occurring within them to either create new drought codes for a specific area or adjust a drought code for a fire station. And you're directly measuring the ground with this, so you can see changes due to lack of snowfall over the winter or midsummer ground thaw. So here's what I mean by large area monitoring is in the top showing Toke Forest from ERS again. But the green box would represent an area we would average all the backscatter values within that. And so each of the blue points on this plot represents one date from one ERS image plotted against the drought code from the nearby weather station. And we did this plot is based on 4 fires, the Delta Junction, not the Dowley Fest, but just the Delta, the Haidukovich Creek one, the Toke Survey Line Fire, and then fires at Anderson. We made a correlation of an R-squared of 0.64, came up with a predictive equation. Also, I forgot to mention those red points on there are from another satellite, RadarSat 1, and from sites in Canada. So you can see that they follow the same trend, and it's from a different polarization, so which you generally get a little bit higher backscatter. So that's probably why it shifted up a little bit. So using this predictive equation, we went into Donnelly Flats, where that was not used in the algorithm, and we did other sites as well. But in this presentation, I'm just showing Donnelly. So we went to a June or a May 2nd image, got the backscatter, put it into the predictive equation to get out the star estimated drought code, which in this case was 281.7. Based on the Greeley weather station, it was 79.4 when they used the default of 15 starting in April. So it was, according to this, underestimating the drought conditions in that region. And then this is showing downley flash from that same year, showing the spring initialization in April. And then the yellow boxes are the radar-derived drought code using that equation. And initializing in the drought code in the spring with the ERS data is the blue line. And then the red line is if we, every time we get a radar overpass, we correct it and restart the FWI, the drought code calculation. Just keep readjusting it throughout the summer. And then these green dots are field data that's been converted to drought code using, I think it was the Dalrymple equation from Whitehorse, taking our moisture data collected on the ground and converting it to drought code. And you can see it matches up pretty well with the radar on some of the dates. There is variability going on from day to date, and they don't always all match the date of the radar with the actual in situ moisture measurement. But there's this general trend of decreased moisture in our in situ measurements, and drought code just has this tendency to just kind of keep increasing. So that's one way adjust this periodically, either just in the spring. It's a problem because it takes 53 days to correct itself, the lag. Do it midsummer. Have additional point locations to increase your sampling area. And then this can currently be done with the Sentinel-1, which is freely available data. I haven't tested it. That satellite just went up last year, but the data started flowing last fall, so that's something which I'm, based on it's the successor satellite to ERS, which I used in this demonstration. It should work fine. And I wanted to shift to looking at the plot scale, because the goal is to try and make a map across the whole landscape of what the fuel moisture is. And this looks at burn sites. I think these were mostly in Donley Flats and Gerstle. Oh, actually, no, this was just all of them, right? All of those 4 fires that I showed. There's a lot of variability between at the plot scale in the moisture versus the radar backscatter, and that has to do with those confounding factors of roughness of the ground and vegetation. And I kind of grouped them here based on burn severity to the ground. With high severity, you tend to remove all of that moss and you have less sprouting of shrubs and more seeding. So you have different vegetation growing back in those sites than you would in a low or moderate. And then if you looked at unburned spruce with this same sensor, you get a trend for each of the different sites, but putting them together is a problem because here the biomass is even greater, so it's even more of a hindrance. But some of the work that I ended up doing with polarimetric radar was to account for the structural variability so that we could retrieve soil moisture. So the hypothesis was that we could use the SAR polarimetry for the structural and it can kind of separate the structure from the moisture variation by looking at the different scattering mechanisms that are occurring. And using polarimetric parameters or decomposition variables to break down the signal into polarization state and be able to retrieve the moisture better.
Laura, can I ask another question?
Sure.
Why does the polarimetric SAR is it less confounded by the surface roughness?
Okay, so I pulled those slides out on explaining it, but so colorimetric radar, it sends out two polarizations that are orthogonal to each other. So in most cases, it's horizontal and vertical, and then it receives all possible combinations. So it gets horizontal send, horizontal receive, horizontal send, vertical receive. Something on the ground changed that polarization. Usually it's higher biomass that changes it. And vertical send and receive, and then vertical to horizontal. And it keeps not only that the amplitude information or the strength of the return, but also the phase. And it changes in the phase that allow you to break down to understand the polarization state. So it's more sensitive to structure. And in a few slides, I'll show a figure that looks at a variable called the maximum degree of polarization. So all the energy that's sent out is polarized, but then it interacts with vegetation in the ground, and what comes back is not fully polarized anymore. And how much vegetation that it interacts with or roughness on the ground affects how much of it is actually polarized when it returns. So
in really oversimplified terms, it kind of works like polarized sunglasses that allow you to see deeper into a lake or a pond or something, because kind of you're getting it from two different angles instead of just a single band, one angle that might hit obstructive canopy.
So they're the same angle. They're just, you've kind of fully characterized what you've got on the ground by looking at the two orthogonal polarizations. So it's related to what you said, but they're not different angles. They're different polarizations is maybe what you meant. So it allows you to kind of recreate what that structure was, basically. And you can, there's a whole bunch of different decompositions that break the signal down into the elements, that the scattering elements. So whether or not it was just scattering from the surface or scattering from the volume of the vegetation, or what we call double bounce from that just hits the ground and the tree trunks, and you get a strong return sometimes if it's really wet back to the sun surface. So you can break it down into those. It's kind of complicated, which is why I left it out. Maybe I should have left it. Does that help explain it a little bit?
Yeah, thanks.
Okay. So basically, I studied this area, the Donnelly Flats and the Granite Creek fires, using data from 2008 to 2010. And I had both burned and unburned, what I called burned and unburned sites. Almost all of them are burned at some point in time, but in the past. But the unburned site, or the burned sites were recently burned, like 15 years or less. So the 1987 burn was considered, it had a lot of woody vegetation, so it was considered one of my unburned sites. So we looked at a chronosequence of black spruce that were regenerating. So we had the low burn severity, where you have a lot of shrubs growing back. These moderate burn severity sites, which are mostly grasses on the ground, and then they had these clumps of shrubs. And then this second moderate burn severity 2 site actually had more regrowth than the other one, and denser shrubs. So the ground was very, very flat, and very little bit of organic soil left. And then we had the shrubby regrowth site. These were what we considered the unburned, and then a sparse spruce forest, and then a dense spruce. So I did 2 types of analysis. I looked at wet versus dry states and just compared both at the shorter wavelength C band as well as L band, the 23 centimeter wavelengths. And I'm only going to show a few of the variables I looked at, but I'm showing the first, I think the next slide, this normalized percent difference. So we took the scattering from the wet date, subtracted the dry date, and then divided it by the wet date, multiplied by 100 to look at the change And then the second thing I did was, for the C-band only, I developed an empirical algorithm to retrieve the. These are the images. They're actually pretty small. They only cover about 20 by 20 kilometers. And then there's a pulsar L-band, which this one is no longer, I think it stopped working in 2011, but there's a successor, pulsar 2, and RadarSat 2. They're both fully polarimetric systems. And so most of the sites were in this Downley or near the Downley burn, and then one over here in the Fort Greely burn. But you can see in the RadarSat and the burn sites, you can see a big difference between the wet and the dry. You don't see as big of a difference in the L-band, and I think the L-band is probably better for the higher density and forests and shrublands than it is for these burn sites. It's so long, I think it tends to just scatter away from the satellite in some cases, or just, it doesn't really see the vegetation because it's so small. So this is looking at that normalized percent change for each of the sites. All the green ones are the unburned sites, and the burned sites are the orange ones. And almost all of them showed an increase in scattering on the wet date, except for these moderate burn severity sites at L-band, where the ground was pretty smooth. So that was a surprise at first, but considering the long wavelength, it's probably not seeing the vegetation there. And the point here was, this is showing, especially for this dense spruce site, you're getting a lot larger change between the two dates because you're getting better canopy penetration at L-band than you do at C-band. C-band appears to be more suitable for these recently burned sites. So the next thing I did was look at a series of C-band images from this area under different moisture conditions, with including the driest and the wettest state, which are on the right. And I developed 3 different models to retrieve the moisture. The one was only the recently burned sites, the second one was only the unburned sites, and the third one was all of the sites combined. Well, the sets of models, I guess I should say, because I didn't just create one. So this is that maximum degree of polarization I was talking about. This top plot is showing all of the sites and how that varies with each color is a different date of imagery. And you can see there's slight differences between these, but between the different dates, but they're all following the same trend. It doesn't appear that moisture really is affecting this variable. I think it's more strongly related to the structure. So using that with a variable like the horizontal backscatter from C-band, which is highly related to moisture status, I worked with those and other variables to try and create an algorithm that would account for both the structure and the moisture change. So then these are just one-to-one plots showing actual moisture versus what was predicted from the top. I was just using that, using only CHH in the model and predicting moisture. And you have a trend, and the green dots here are validation, the blue are what were used to make the model. There's a general trend in each of them, but quite a bit of spread. And the middle one is using all 4 of those channels, not the polarimetric, but just the backscatter, the amplitude information. And in some cases, it might make it worse. In some cases, it makes it better, like the burn sites, it makes it a little bit better. And then using the polarimetric parameters in the model improves it a lot. The standard errors go down, and the RMSE errors also go way down. It actually improved these models over these set of models were improved by 27 to 32%, depending upon the model. So then I used the model that was for all sites and mapped moisture in these areas that had lower biomass, because C-band is better for the lower biomass. So the first one was a wet date. This is a moderately wet date. And the bottom one is the dry date. So the goal is to be able to do this across the unburned areas as well, and that's where my research left off. It looks like there's a strong utility for accounting for structural complexity by using the polarimetric radar and combining those variables that are strongly related to structural complexity with those that are strongly related to moisture, improve the algorithms quite a bit. The next step, I've got a series of Palisar 2 images, not from that area, but from unburned forest over near the Hajdukovich Creek fire. So I'm working on those, trying to analyze those, hopefully be able to make a map of moisture from those, and keep working on this research to bring it closer to being useful operationally eventually. So we talked a little bit about SMAP, which is the NASA satellite that went up in January, and it has the active and passive. So it has a 36-kilometer passive microwave sensor and a 3-kilometer active. And then they are creating a combined product, taking advantage of the high resolution of one and the coarse of the other. There's been a lot of research saying that passive microwave is less sensitive to vegetation and roughness. So the combined product should be better, should be higher resolution, but taking advantage of both of those sensors. And then the 3-kilometer radar only is a research product, so they're going to evaluate it. I don't know that they're going to produce it globally unless it works. It hasn't been tested as much. And the thing about the sensors, it'll collect globally every 3 days. So even though it's coarser, but it could provide some really useful information if you can get it every 3 days updated. And we're actually putting a proposal in, and Randy's a collaborator on that, to evaluate these products, both the 9-kilometer and the 3-kilometer products, and try and relate those across boreal and Arctic North America to fire weather index codes, as well as a network of moisture stations that exist. And then we had planned to set up some more intensive sites, one in the tundra near Tulik, one in peatlands in Alberta, and then our collaborators at Canadian Forest Service, we're going to do some in northern Ontario, more upland boreal. Hopefully we get funded and we can integrate that into fuel moisture monitoring, health management. And fire, I think it should help a lot. I know it's coarse resolution, but it's high repeat, so I have high hopes. That's it. These are just some of the publications that I've had from this work, more recent ones. The older ones are none. Do we have any questions?
One comment to go with that last slide about the SMAP data. Some folks might not know or might be interested to know that the Alaska Satellite Facility at UAF is the national downloading point to bring down that satellite data. So they're actually calibrating the data right now, and they'll be producing the level 1 products and sending those down to, I guess, JPL or wherever they get processed in the lower 48. So it would be really appropriate if we had some data on the utility of this, a study going on for Alaska fire management because we're the first ones to get the data and should have the least latency, at least for the level 1 products.
So, a question with this last one you're talking about with the SNAP and proposal you're putting in. Have you also included Robert Zeal as somebody to collaborate on that?
Robert. No, I don't know Robert.
Randy? Just thinking about what he's been doing with some of the other stuff for us, he might be useful. At least somebody for you to talk to. So.
Yeah.
And I'll send him a copy of this presentation.
So, are we actually have to have the proposal done tomorrow?
Okay.
But
it might be a little late then, but when you're actually
if we can have a CV from him and his input, we can add him. But it would have to be by end of day tomorrow.
Okay, it might be a little late, but I'll talk to him.
Okay. What has he been doing?
He works for the state, but he's been doing a lot of our fire weather index and dealing with a lot of the trying to figure out how to integrate other systems into this so that we get better representation across a landscape rather than the paintballs.
Okay. Does he work with Sharon then? Or?
Yes.
Okay.
So one advancement we should see this season is instead of the paintballs where we just have the point data on FWIs, there's going to be a gridded FWI product that would be across the whole landscape that, of course, uses gridded weather data with the potential sources of air contained in that, but still it'll be a wall-to-wall coverage of FWI data, which might be something useful.
That's what he's doing?
Yeah.
Yeah, he's working with a company called Muso West, and they're actively putting data on their website right now for that. Another very useful thing will be archival information on FWI indices. So, some of your studies you used retrospective data, and now that'll be more easily available. You'll be able to get that retrospective data on FWIs from previous fire events or dry periods in the past and that kind of thing.
So what does he use to grid this then? Is it a model, like a weather model, or?
Yeah, it is. Geez, I've heard this presentation several times and I still can't tell you what the weather model is. Eric?
Yeah, I'm not sure exactly either.
No. How about, just in the interest of time, we'll get him connected to you because we're about 3 or 4 minutes from the end of when this call is scheduled to end.
Okay.
Okay?
That's fine.
Yep. So thank you very much for taking the time to put this on, and it looks like a good way to be continuing to move forward and then figure out how to extend it out of the boreal will be really good.
Yeah, I'm interested to see what Robert was doing, and that actually might be a good thing to compare SMAP to.
Yeah.
Instead of just points, or we can do points and his grid.
Yep.
It combines both the coarse resolution passive with a high resolution active sensor to get 9 kilometer resolution. So everyone on the call knows about the
Hello?
Yes.
What? Is it?
I don't know what that was.
There's a bad connection. I don't know if the question was for me. I didn't understand the question.
I have a question for you, Sarah. Is 1 hour drop dead? I saw Jessica had reserved the WebEx for an hour and a half. Is there any thing going to happen if we run over a few minutes?
there's nothing else scheduled immediately, but we usually wrap up in an hour. But there's no reason that people couldn't stay on the line and ask Laura some more questions. I do have a question. We have one person on the phone or on the line who I think is new to the team, Chris Wagle. Are you on the call?
You might be on mute.
Yeah, Chris is a meteorologist and scientist at UAF in the International Arctic Research Center, and she would be the one who could answer that question we had about which weather model is being used, probably. But
well, I see her on the WebEx, but maybe she's not linked in to audio. I'm not sure.
Right. Yeah.
So, but in answer to your question, the line will be open, and those who wanted to stay on could. I don't think we have anything else scheduled. We do have something scheduled in a half an hour, in 30 minutes.
Okay, then I was wondering, Laura, if you could just briefly, what are you going to do in Northwest Territories this year? I'm kind of interested in that.
So that's a pre-above grant, kind of a rapid response to those fires, and we're only funded to collect field data there. That's critical information to collect 1 year after that fire, and also to prepare some kind of preliminary products. So we've created from MODIS hotspot data fire progression maps for a series of fires there. And then we've been working on creating peatland maps so we can make sure we visit fens and bogs and as well as uplands. And then the other product, we've been working with Ron Hall from Canada, and he created the NBRs for each of the fires. So we're using those to kind of determine that, and also information on ecoregion types. So we have the taiga plains and the shield. So we're trying to get sites on both, as well as sites that have permafrost and that don't, and trying to get just a range of seasonality of fire to try and sample. In June and July this year. So we'll just be collecting data on burn severity using methods that were developed by Viereck and Dernis and Norum for the 5-point scale to the ground. We'll also be doing depth for fuel consumption, depth of consumption of the organic soil layers, and characterizing the burns and measuring soil moisture in a series of them. Then we have RadarSat-2 being collected in both June and July for a series of sites. So we'll measure the moisture and then also the revegetation in those sites, whether they're sprouting or seeding in, and then the diversity of the vegetation. We're trying to work with some other people that are going to be out in the field, and so for remote sensing, our plots are usually pretty large. We tend to do areas that are 200 by 200 meters, try and characterize them with some smaller plots within that. And some of the other people that are more interested in just the vegetation are doing like 1 meter plots along transects or things like that. So we're trying to kind of nest it so that they're sampling within our 200 by 200 so we can use each other's data. Yeah,
will you be doing the CBI plots like the Benson and Keyes CBI plots, or a modified version of that for Delta NBR?
We weren't using that. So in the past, when we did some work in the peatlands in Alberta, we did both CBI and the Viereck method, as well as something similar that Eric Kaczynski developed for the canopy. And they are more strongly related to the Landsat than the CBI parameters. But more importantly, we were doing it for carbon emissions, and the fire manager, Bill DeGroot, who runs the campfire model, he said that the CBI metrics are not useful for his model.
That's interesting.
And so he used our burn severity index that we created, which was just, so there are 5 classes of severity to the ground using the VERIC method, with 0 or 1 being unburned, 5 being severely burned. And you kind of do an assessment on an area, a plot area. So you have percentages within each of those classes. And we
Right.
had really good correlation of that to Landsat. That's what we were interested in. The ground is what the question is about, you know, how deep are those organic soils burning? How is it affecting?
Yeah. It's not too surprising that would be a little bit more related to the consumption, actually, so interesting.
Overstory? I mean, of the canopy and...
No, consumption of the surface fuel and organic layers.
Yeah, what would be more related to that, the CBI?
The VERIC sort of 5-class index.
Oh, yeah, it's more related to that, and that's what they needed for the campfire. I know other people will be, Ron Hall and his people are going to be, and actually we're discussing with them now because it's not that much more work to do it. But we do have limited time, so we're working with a team from University of Alberta right now trying to decide what metrics we need to sample in the field so that we can help each other out. They're more interested in the canopy. They're also more interested in the uplands. We're more interested in the peatlands. But if we can use each other's data, that would be very valuable. So we just exchanged this morning. We exchanged our field sheets, and we'll decide before we head up there in June.
That's great. Are there any other questions for Laura?